So a couple announcements that I have. Make sure that you submit part 2 of the intermediate project by preferably the end of today. I mean, ideally it would have been before 3 p.m., but there's no hard deadline, so just sometime by the end of today. Because later today we'll also be sending out part 3 of the intermediate project, or Elliot will. So he'll be sending that out shortly, I think. And this part is a little bit longer, so you're gonna have 2 weeks to finish it up. So it'll be due I guess right before spring break. Yeah, or right at the start of spring break. Today's lecture is on linear algebra and a simple introduction to linear regression. If you've taken Math 54, the first half is going to be pretty much mostly review of stuff that you should already know, basic matrix operations, things like that. For most of the rest of the semester, that's what we're going to be dealing with a lot. A lot of some of the supervised learning algorithms that we're going to talk about require a decent amount of linear algebra knowledge. So it's really important that you have a strong grasp of matrix multiplication, things like that today. So if you haven't taken Math 54, make sure you pay a little bit closer attention to the first half. Otherwise, the second half is a little bit more important for those of you who maybe already have taken Math 54. So any other announcements before we get started? I know that the current video situation is not quite ideal. Well, I don't know, maybe for some of you it is. Being able to skip half of the lecture and not pay attention, which makes me a little bit sad. But it's definitely not ideal in terms of meeting other people in the club and getting to attend social events, things like that. Everything got canceled this past weekend, and things probably will for the next couple weeks. So we'll probably have the next few lectures done like this. If you have any suggestions, comments, concerns, just message me, and we can work through some stuff. But otherwise, we have Harry. Wait, Harry, slide this way a little bit. Okay. So we have Harry and Yiming who will come up later to teach you guys a little bit about linear algebra.
So today we're going to learn about linear algebra. So we're going to go into some of the mathy part of it, so we can understand what's going on behind the code. So before we talk about matrices and vectors, we should talk about what scalars are. So scalars are just numbers that you would typically think is part of the real numbers. You can just do, it's sort of the numbers that you've been working with through your pretty much most of your math classes. And so using scalars, we can build up vectors. So there are two main types of vectors. There are row vectors and column vectors. And so we have a vector, and we can call this x1 all the way down to xn. And so, oh, I should write it here. So we have two types of vectors. So we have column vectors and row vectors. And you can think of, no matter what type of vector it is, we can think of each vector as sort of a collection of entries. You think of these as just an ordered collection of scalars. So each number here is from the real numbers. So xi is from the reals. So vectors are just single-dimensional collections of scalars. And we'll get into what a dimension is later. But what I want to talk about next is matrices. So matrices, as you probably know, sort of rectangular in shape. And so you can think of each column as a separate vector. So each column is sort of like this vector here. And so that's something to, I guess, like simplify. So vectors are collections of scalars, and then matrices are collections of vectors. So that's like the easiest way to think about it. So now that we know what matrices and vectors are, we can talk about like the shape or size or the dimension of it. So yeah, so basically the shape is just the number of rows and number of columns. So for this vector, we have n entries. So this would just be an n by 1 matrix. And it's usually, okay, so it's pretty, it's convention that we write the number of rows first and then the number of columns. So for a row vector, it would just be 1 by n. For a matrix, similarly, if we have, let's say n rows and, let's say we have m rows and n columns, then this would just be an m by n matrix. And so this is what we mean by the shape and size. And then, so before we move on, to introduce some notation, so so to introduce some notation, let's say just any variable. I'm talking about a scalar. Any lowercase variable that I have an arrow over, that will be a vector. So this would be our n. So n would just be the dimension. And any capital letter that I use, that will be a matrix. So scalar, vector, so yeah, now we can talk about some of the more interesting cases. So the first matrix that I would like to introduce to you is the identity matrix. So the identity matrix, we can think of this as a square matrix, meaning there are the same number of rows and the same number of columns. And the identity matrix is sort of a matrix where you can construct where all the ones are on the diagonal. All the diagonals are ones, and everything else are zeros. We call the parts that aren't on the diagonal the off diagonals. And so for a lot of these examples, I'll give 2 by 2 matrices just to make something, just to make these abstract concepts a little bit more solidified. So, so this would be a 2 by 2 identity matrix. 3 by 3, it would you just add an extra column, you just tack on an extra column and row and have one at the very corner. And we'll get into why this is useful. Another thing to note is that sometimes, so the identity matrix is usually denoted as I, capital I. If you want to be a little bit more specific, you can denote the size of the identity matrix with a subscript. So in this case, it's a 2 by 2 matrix, so you say I sub 2. Yeah, and the more general case would be I sub n, and that would just be n rows and n columns. So yeah. Okay. We mentioned that the identity matrix is a square matrix. So what that means is we have the same number of rows and columns. So identity matrix, since just by definition is a square matrix. However, in another example of like a square matrix could be like, let's say like 1, 2, 3, 4. This 2 by 2 matrix. Square matrices have nice properties, and we can talk about that a little bit later. Okay. So one other sort of terminology that I like to introduce is the rank. We'll talk about that later when we talk about linear independence. So just keep in mind for that. So now that we know what matrices are, so does anyone have questions about like I guess like the terminology? Yeah.
Can you write down the vocab word somewhere?
Sure. Yeah. It's on the
It's in the notebook.
Yeah, it's in the notebook.
It's listed in the notebook.
Yeah.
It's on the whiteboard, blackboard, brownboard.
Do you want me to write it down?
Yeah, if you could just write them all quick, yeah.
Cool.
Well, you already have 3 of them there, I guess, but.
Yeah. So yeah. So I'll write down the ones that I covered so far. There are more, but I'll cover them a little bit later. So we have so I is going to be identity matrix. Size shape. That's the so for an example of an identity matrix would be something like this. Size and shape. So we have number of rows times the number of columns. So for example, 2 by 3, the 2 by 3 matrix. This is just something like 2 rows, 3 columns. So let's say 1, 1, 1, 3, 4, 5. Okay. Did I miss anything else? So I guess I could also write down the row vector and column vector. So so a column vector is just a vertical column, size n by 1, and then row vector. Okay, so next we'll talk about operations that we can perform in matrices. So one of the most simplest ones is the transpose. So with the I'll give you an example first before I talk about what it is. So transpose we denote, so let's say A is a matrix. So the transpose we denote as tiny t as a superscript. And so let's say A is 1, 2, 3, 4. So transpose, I sort of think it as like a flip. So we can think of, so A transpose would equal the diagonals, so since this is a square matrix, we keep the diagonals. So this would be 1, 4, then this would be 3, 2. So if it's a square matrix, you sort of just reflect it across the diagonal. However, transpose can also be applied to non-square matrices. So let's see an example of that. So let's say A is equal to a 2 by 3 matrix. Then let's say it's 3, 4, 5, 0, 0, 1. Okay, and the way I like to think about when I construct the transpose is I go down a column and I fill out the rows. So now the transpose so the size is 2 by 3. The transpose will be a 3 by 2. So it's always the case that the transpose flips the size. So it flips the number of rows and the number of columns. So in this example, let's go 1 column at a time. So 3, 0, I fill out the first row. 4, 0, I fill out the second row now. Third column, third row. And this is our transpose. So now one of the cool properties about the transpose is that let's say we have A transpose. Let's take the transpose of that. Now what this is, you get back the original matrix. If you wanna see why, or let's continue this example. So A transpose transpose. Let's go by each column. So the first column, 3, 4, 5, let's fill out the first row, 3, 4, 5. And the second column, let's fill out the second row, 0, 0, 1. And now we have the same matrix. So those are transposes. Does anyone have any questions about transposes? Okay. So now that we know what transposes are, let's talk about addition and subtraction. Okay, I'll erase this. So addition. For addition, it's really crucial that the size of the matrix corresponds with each other. So let's say we want to add two matrices, A plus B. So let's say A is a M by N matrix. B also must be an M by N matrix. So for example, let's say that A is a 2 by 3 matrix. So 2 by 3. Let's say 0, 1, 5, 2, something like that. And let's say B is equal to something like 1, 5, 5, 2, 2, 1, something like that. So we can add matrices together such that we look at the two. So we add them up entry-wise, meaning that if we take the first row and first column, we have to add it with B's first row and first column. So what A plus B equals, this is just, so 0 plus 1, 1, 1 plus 5, 6, and so on, 6, 5, 3. Yeah, and so since matrix addition the definition of matrix addition is to add matrices entry-wise, it wouldn't make sense if it's a different size. So for example, let's say B was just a 2 by 2 matrix. Then what happens to the third column? Then we can't really add it together. So that's why we have to have the two sizes to match. And so using what we know about transposes, I'm not going to show it here, but a property of addition and transposes is that A plus B transpose is equal to A transpose plus B transpose. Yeah, so I'm not going to show why that's the case right here, but just know that this is one of the properties that combines addition and transposes together. Okay, and likewise, we could also change this to a subtraction as well. This would also work. So it doesn't have to just be addition, it could be a subtraction as well. Yeah. Okay. And then next we'll talk about scalar multiplication with matrices. And so let's say so let me give you an example first. So let's say we have the identity matrix. We multiply that by 2. What scalar multiplication with matrices does is that you just take whatever scalar is here we multiply it with each entry. So what this is 2, 0, 0, 2. And so this is what is known as a scalar matrix. And so what a scalar matrix is just any sort of constant multiplied by the identity matrix. And yeah. Of course, we can do this with like other types of matrices as well. This could be a 2 by 3, 3 by 3, or any sort of dimension. And so the more interesting case, now what if we multiply two matrices? Well, two matrices, like addition, there is some sort of like restriction on what you can multiply. And the main restriction is, so let's say we have A times B. Say that A is n by n, and B is n by p. So this only makes sense. If the two dimensions in the middle are the same. And the resulting, let's say this is C. The resulting matrix, that dimension will be the outside ones. So this would be n by p. Okay. To give you an example, let's have a scalar matrix. So 2, 0, 0, 2. Let's multiply this by 2, 4, 5, 6. Okay. So for each row, you want to multiply on the column of the second. So you want to multiply the first. So in the first matrix, you want to take each row. You want to multiply by each column in the second matrix. This is what's known as the dot product. If you're not familiar with it, it's okay. I'm going to do an example right now. So take the first row of the first matrix, first row of the first column of the second matrix. So 1 times 2, 2, 0 plus 4, 0 times 4 is 0. And we just add those two products together. So that's just 2. Let's draw out this matrix first. So this is a 2 by 2. This is a 2 by 3. These two match, so we're good. The dimension of the final resulting matrix will be a 2 by 3 matrix, which is just the outside terms. So you have a 2 by 3 matrix. So we multiplied first row, first column. 1 times 2 is 2, plus 0 times 4 is 0, it's 2. Okay, let's do it for this one. So 2 times 2 is 4, plus 0 times 5 is 0, so this is 4. Keep doing it. 6, it's 8, it's 10. You can finally do this, which is 12. And this is our resulting matrix. So, as you probably know, when we deal with just plain numbers, so like 2 times 3 is equal to 3 times 2, but in matrices, that's not the case. It's sort of surprising, but the intuition is that since matrix multiplication only makes sense if the two terms in the middle match, let's say if we switch it, let's say it's B times A, that wouldn't make sense since the middle two would then be P and M, and they don't match. They don't necessarily match. So to make this a little more clear, I'm gonna erase this. So generally, A times B does not equal B times A. Although sometimes they may equal. One example is if they're inverses, but we'll talk about that later. But generally, these two do not equal each other. Okay. So to connect what we learned about transposes, A times B transpose is equal to B transpose A transpose. Again, I'm not going to show this, but this is just this is true all the time. Okay. So does anyone have questions so far? Okay. So then we'll talk about linear independence. So what does it mean to be linearly independent? Well, I'll give you an example of what it means to be linearly dependent first. So linear dependence. So let's say we have a vector. Let's call this x. X is a vector 1, 2. And let's have another vector, which is 2, 4. Okay. So we notice that 2 times x, so y is equal to 2 times x. And because we can construct y from x, x and y are not linearly independent. They're dependent because there is some sort of relationship such that you can construct one from the other. So what it means to be independent is that you can't construct y from any set of vectors that you're given. So this could be like, we have like n vectors, each having, I guess, p entries. And for them to be independent means that any subset of vectors cannot construct any other vector in that set. It's sort of abstract right now, and we have like software to do that like automatically. But this is sort of what it means to be independent. So, for example, in this example, since we have linear dependence, we could just, I guess, change this to like a 5. And this would be linearly independent. Because there's no way that we can construct y from x, and there's no way for us to construct x from y. Okay? You can generalize this with like vectors of like greater number of entries, and with more vectors as well. But like it's a little bit more complex, and might not want to get into that right now. Okay. Okay, so the last big hurdle that we have to go through is inverses. So like inverses when we deal with like real numbers, what we want is a matrix such that, let's say A is our matrix. We want a matrix A inverse such that this is equal to the identity matrix. You can think of like the identity matrix as like analogous to like 1 in the real numbers. It's also the case that A inverse is equal to I as well. So one thing to note is that for there to be an inverse, so sometimes this might not even exist, and that's okay. So it might be the case that A inverse doesn't exist, and we'll talk about when it does in a bit. So yeah, one sort of condition for an inverse to exist is to have A as a square matrix. We'll get into why that's the case later as well. So yeah, so so I'm going to list out when this inverse exists, and so all right. So A inverse exists if 1, A is square, 2, is a determinant of A, not equal to 0. And so the determinant. What is the determinant? Well, I'll show you in a 2 by 2 case for a matrix of greater dimensions. It can get kind of messy. And also to note, determinants only work for square matrices. So the determinant is as follows. So let's say A is A, B, C, D. Determinant A is equal to, so the determinant of A is equal to A times D minus B times C. Yeah, so from this, if this is 0, this means that A inverse does not exist. The reason for that is for a 2 by 2 matrix, so for 2 by 2 matrix, here's how you calculate the inverse. A inverse is equal to 1 over the determinant of A times D A negative B negative C. Yeah, so a really nice exercise, if you want to just try it out, is to just take these, like, I guess, variable forms, multiply them together and see if you get the identity matrix. Thanks. Again, we have another property that connects inverses with transposes. So transposes, so let's say A inverse transpose is equal to A transpose inverse. Yeah, so this is again one of those properties that may be very useful, but I won't be proving that here. So why do we care about inverses? Well, when we do linear regression, the equation actually involves taking inverses of matrices. And in certain situations, we want to know when we can take the inverse, when we can't. There are a lot of implications of when we can't and when we can. And also, when you run software to do linear regression or any sort of, I guess, like machine learning packages out there, you want to understand what the errors might be outputting, what the errors might be saying. And a lot of those errors have to deal with linear algebra. And this is why we really want you to understand like the math behind the things that you're doing on the computer. A lot of it has to do with inverses. So while he's getting that, I guess for what do you want to learn about linear algebra? Well, it's not just useful in stats. So in stats, we use them mainly because, well, data is arranged in tables, but tables themselves are matrices themselves. So you can think of each row as like an entry, like I guess each person, each sample, and the columns would be the variables. You can so knowing matrix properties, we can determine like certain patterns in data and things like that. This also applies to like other fields like econ and like even physics as well. Thanks.
How does that work though with the stuff in a data table isn't numbers?
Yes. So we'll actually talk about that later, right, Andrew? Like categorical variables.
Probably next week.
Yeah.
Not today, right? You mean? Yeah. So next week. Next week we'll talk about that a little bit. Yeah.
Yeah. So I guess the simple case would be if let's say you have let's say like the variable that you have is like what let's say it's like heads or tails. It's those are like I guess like those aren't numbers, but you can assign numbers to them arbitrarily. So you can say like tails is 0 and like heads is 1. It gets a little bit more complicated when like variables are like when there's no like I guess order to them or when there are more than 2. Example would be like if I ask like a bunch of people their favorite color, how do I assign numbers to that? Because if I assign numbers, then that means there's some sort of like ranking system, and so we'll get into like how you deal with that a bit later. Yeah, thanks for asking. Okay, so now we'll get into the Jupyter Notebook. Okay, okay, so I'm in the scalar multiplication section, right under matrix operations in NumPy. Is everyone there? So what I typed was just a times 5. You can switch the order as well. You can be 5 times a as well, so it doesn't really matter the order. If you try that for yourself, then you can see a matrix that's being outputted. That is exactly a scalar multiplication with matrices.
You write an X?
Hmm?
You write an X?
Oh no, the little asterisk symbol. Yeah. Now let's get into matrix multiplication. So matrices. What we can do is, so to multiply A times B, we would have A and then the at symbol, and then B. And that should give you the resulting matrix, the 3 by 3 matrix that is exactly the product of A and B. And you can actually try it for yourself. Since I told you to write A at B, you can try B at A, and you'll see that you'll get different matrices. So that shows that multiplication with matrices is not commutative. Okay, and now let's try matrix inverses. So this is, I'm going to write the command on the board. So those of you following along, it's empty the thing out. That should give you the inverse. So empties out linalg dot inverse, and we get an inverse. Yeah. So let's try that with B, and we get the inverse of that as well. Okay. So next we'll talk about linear independence, and so for square matrices, actually, so I forgot to mention this, but for square matrices, the determinant actually tells you a little bit about the linear independence. So if the determinant is 0, the columns are not linearly independent. So that also means that for there to be an inverse, all the columns must be linearly independent. And so what we can do with a square matrix is we can just calculate the determinant, and that can tell us whether a matrix is invertible or not. So let's type in np.linealg again. Instead of .inv, we're going to type .det. So yeah, should get a number close to 1. Okay. So yeah, that's how you calculate the determinant as well, I guess. So next we'll talk about transpose. Transpose is just the matrix name and then a capital T. And you get the transpose of A. No? Okay. Yeah, you can try it with B as well. You could try to take the transpose of the transpose. You can combine these sort of commands together into some longer expression, something a little bit more complex. These are just the building blocks. Yeah. Does anyone have questions? Yeah.
What's the code again?
For
The transpose?
yeah. So it's your matrix name and then a capital T. And yeah. Now Dean will take over. Okay, go ahead. Yeah, that's right.
Okay, so now we're going to talk about linear regression. So we're going to start by what a model is, and by talking about what a model is, and then we're going to move on to talk about linear models and the assumptions that we make when doing linear regression. So a model is really just a simplification of the real world. You want to capture some relationship between the two variables you see in the real world by trying to fit a theoretical model to the data. So if you scroll down a little bit, you will see that there are 3 straight lines passing through this data cloud. And you might think that one of them is probably better than the other 2. And we're going to actually give you a very strict formal definition about how to identify a better model and how to identify the best model actually using the data that you're given and using the loss function that you're given. So why do we want to make a model? We want to make a model because a lot of times many real world problems are really complicated, but if you were to extract some information from it, they can be really easily solved, and you just want to understand the relationship between 2 of the variables. You might have heard the phrase that correlation does not equal causation, and a very famous example of that would be the ice cream sales and murder rates are linked, and there's a very positive correlation between the ice cream sales and the murder rate. That does not mean you should not eat ice cream. It does not make you a murderer if you eat ice cream. It also does not make you less of a murderer if you don't eat ice cream. Chill, Ronnie. All that is just to say, even though there might be a positive correlation or a negative correlation, that you may think there is a relationship, it does not mean that 2 things, one causes the other. Although sometimes you can use other form of regression or other form of method to study causal effects, and usually that's called causal inference, and you can, of course, learn more about that if you're interested. Okay, but for the linear models that we're talking about today, we're purely interested in correlation, meaning how correlated are my 2 variables and not if one causes the other. Okay, so linear regression is just a method of making linear models. And linear model is just like you assume that the relationship between your response variable and your explanatory variable is a straight line, basically, in the simple 2D case. Or you think that they're connected by some sort of high-dimensional hyperplane in the higher dimensional case. For today, we're only talking, yes?
What's a hyperplane?
A hyperplane is a plane. It's defined by W transpose Z, where Z is a normal vector and, okay, never mind. don't worry about hyperplane. For today, we're talking about a straight line, which is the simple linear regression. Andrew will talk about multiple linear regression next time. So you can ask Andrew what a hyperplane next time. So Andrew's not happy about this. Okay, so simple linear regression has the form of y is equal to theta naught plus theta 1x, just like how you would expect from a straight line. And then in real world, because our data is noisy, we're assuming that there's some error in our measurements, so our data are not perfect. So in real world, what we see is actually, when we measure, is theta naught plus theta 1x plus some small epsilon, where my epsilon is the error, and it's a random variable that we assume to have some distribution. This has a mean of, let's just say, if we assume that it has a mean of 0, and it has a variance of sigma squared. In the simple linear regression model, if you were to scroll down, you will realize that we assume that all the variance of the epsilon for every data entry is the same. And we actually also assume that my epsilon follows a normal distribution. So my epsilon is actually normal with mean 0 and variance sigma squared. Okay, but before that, the goal of the linear regression is to really extract the best estimate using the data that we have. Whoa.
Are you too small?
Then you do it.
Is this a rig?
It is also too small.
Wait, where is the sensor? By the door.
Next to the door.
Oh. Okay, well, welcome back. So, the goal of the linear regression is really, we're trying to figure out the best parameters, theta naught hat and theta 1 hat, from the data that we have. Note that we're putting a hat in front, on top of everything because we can't recover the true parameters from the data because we have this noise variable, right? If, let's say, what we measure is actually theta naught plus theta 1 times xi, then sure, we can get the actual parameters theta 0 and theta 1. But because we have this noise in our measurement, we actually cannot recover the true theta naught and theta 1, which is why we're putting a hat in front of everything, sorry, on top of everything, to say this is our best guess. This is our estimate of what the parameters are. So knowing that, we're gonna look at the model assumptions. So there are 4 major assumptions that we make in this linear regression model. The first one is, of course, linearity. We're assuming that the variables follow a linear relationship. So the response variable and the explanatory variable has a linear relationship. Note that this means they're linear in the coefficients, meaning that my theta 1 is really just a linear function. Well, it's a linear function of theta naught and theta 1. So you can write it as f theta naught theta 1. So it doesn't really matter if you have the xi squared here. Yes.
What does linear in the coefficients mean?
It just means your linear function is a plus, well, yeah, it would just be like a theta naught plus b theta 1 plus c. So it would just be an additive model.
Does that mean that the variables are linearly correlated to it?
What?
Does it mean the variables are linear to each other?
Are linear to each other.
Andrew,
What was the question?
you asked the question. What does it mean for the coefficients to be linear in a linear model? I.e. not variables. I.e. you can have degrees of the variables.
Yes, we'll talk about that later.
You asked the question.
So the question was, what does it mean for coefficients or variables to be linear in a model? So why is the x in that second line there not linear, but then the theta 1 is? When we talk about like a linear model, we're talking about linear in terms of the coefficients. So we're talking about linear in terms of the thetas there, not in terms of the x's. So the x's can have degrees on them, but those thetas cannot. Other nonlinearities would be like sine or cosine, but you don't need to worry about that too much for now. We'll talk about that in the next 2 weeks.
Tell her about to stop. But anyways, so remember it's linear in the coefficients, so which is why sometimes you will have a polynomial regression, and then even though your terms have like degrees on them, or even sines and cosines and log functions on them, it doesn't really matter as long as they're coefficients and linear. And the second assumption we're making is homoscedasticity. This is a very long word, hard to spell. So it just means the variance and the error terms are the same across all the data points. So in this graph that I'm showing you, in your notebook, you can clearly see that the variance of the data point is clearly increasing as your x value is increasing. So this is an example of heteroscedasticity, where your variance for the error terms are not the same across all the data points. The third assumption we're making is independence. Just like what Harry said, we want the matrix to be full rank so we can invert them. So we're trying to make sure of that by forcing the features to be linearly independent. The fourth assumption is normality, so we're assuming that in the error terms actually follow normal distribution, just so we have some nice results from the theoretical standpoint, and makes our life a lot easier when you assume normality of the errors. Okay, so now we're moving on to the least square error. So we talked about earlier that of the 3 lines that you saw, one of them is clearly better than the other 2. And we're gonna put a notion on what's the best fit line and how do we get that. So usually to get to the best fit, we're gonna define a loss function, meaning if I were to not fit a data point perfectly, how do I want to define the loss I'm incurring by not fitting the data point perfectly? And the common loss function that we're gonna talk about is called the least squares. Sorry, the squared error loss. So it just means, so if let's say my data point is actually yi, and then my prediction from my model is going to be yi hat. Again, I'm putting a hat on it because this is my best guess. And then the squared error just says I'm squaring the deviation. We're squaring the deviation here because a quadratic function that looks something like this is really nice, and it has a global minimum, and which is really easy to optimize when you're trying to do optimization on your computer or by hand. So we're just talking about the least square here, but there are also other loss function out there that you can use for different regression that you can look up if you're interested. Well, we're using the least squared loss here, so that means if I want to find my best model, I really want to minimize the loss I'm incurring. So the total loss for a model is going to be the loss for every data point, and then I'm just summing it up. So the total loss is just going to be the sum of errors, where again my y hat is the prediction and my y's are the real values that I observe in real life. So to minimize this loss function, we're going to rewrite my y hat as a function of thetas, because again our ultimate goal is to find the best parameters theta that optimize my model. So we're going to replace everything with thetas. We're going to replace y hat by theta naught plus theta 1 x, xi. And then we can do some fancy calculus, or not so fancy calculus in this case. If you were to take the derivative with respect to theta naught and theta 1, you're going to get don't mention the word gradient. So if you were to take the Ronnie, I'm not answering your question what a gradient is because I'm not saying the word gradient here.
Can you draw bigger or darker? It's kind of hard.
Okay. Do you want me to rewrite everything?
No, it's okay. Yeah, it's fine.
Perfect. Okay.
That's false.
Okay, well, if you were to take the derivative of this with respect to theta naught and theta 1 and set that equal to 0, then you will get to the ultimate best guess, so the point that minimizes this loss function. Does anyone think they need time with this? Yes. Okay. we still need more time? Okay. So the variable that I chose, I'm gonna use displacement. So I'm gonna put in x1 as displacement, but wrap it in quotes. And I'm gonna say y1 is mpg, but again, wrap it in quotes. And then when I plot a scatter plot, I would just say plot.scatter x1, y1. And we'll see a beautiful scatter plot. And then now we're going to try to fit a model to this. So the way we're fitting a model is by using sklearn library. We're going to import linear regression here. And then you want to define your x and your y. So you can either pass in a matrix or pass in a data frame. So here, let's just pass in a data frame. And the way I'm going to do it is by doing mpg, selecting the displacement, and then the y variable is mpg. Then again, I'm wrapping it in double brackets to make sure I'm passing in a data frame. Okay. And then we can look at the coefficients that intersect. So my theta naught and theta naught hat and theta 1 hat here. So you will read some values of theta 1 and theta naught. Okay, so now we're going to define a function that overlays the simple linear regression model, so the best fit line, on top of the scatter plot. So we're going to define this function and give you maybe a minute or two to think about how you should define this function. Yeah. Can we use a projector? Should
Yeah,
we use a projector?
Might as well. Are you done with the board?
Huh?
Are you done with the board?
Yeah.
Okay.
Ah.
Nice.
Okay. Okay. So the way we're gonna make this line is we're gonna generate a series of points in x, and then we're gonna predict using these points. So what we're gonna do is we're gonna do predict on x, and then we're gonna plot a scatter plot using our variables in the original data frame. And then we're going to plot the line on top of that. So we're going to do p.plot x and y. And just so we can see better, I'm going to do the color with this red here. Oops. And then this should be our function. And when I want to overlay them, I'm going to pass in my x name as displacement. And whoops, okay. Let's see. A little bit wrong. Oh. Wait.
It's lowercase. You made a lowercase x there.
Oh, yes, you're absolutely right. Ta-da! Okay, now we have the best fit line through the data cloud, and this is again achieved by minimizing the sum of squared errors using the formula that we derived earlier above. So if you want to check those, you can also get the coefficients and the slope of this linear model and double check that these numbers actually match the formula that you will get if you were to use it. If you were to use a formula to derive the numbers yourself. And we're not going to talk about interpreting a model, and because Andrew's going to do that next week. Okay, well, but that's it. Is there any question about this last part? Okay, if not, that's it.